In this video, I'm going to talk about non-free fall. Let me share the screen again. Okay, so non-free fall. Let's see. What was the condition for free fall? When do you say the object is in free fall? Object that in falling or it's being thrown up in the air without ignoring the air resistance. So therefore, the only force exerted on the object is gravitational force, and such a condition is called free fall. Then non-free fall is the case that you have to consider air resistance. Air resistance is large enough that we need to take into account, and object is in non-free fall. So today we're going to talk about non-free fall. So that's when air resistance cannot be neglected. Air resistance cannot be ignored. So the net force in such a case is you have still have a gravitational force, and there is air resistance. Air drag force, air resistance. You can also say air drag force. So this is type of resistance, but it's not the same as the resistance that we did between the two solid objects. Now we have an object that's in the air, and that air gives some kind of a resistance. Let's discuss about this air resistance in detail. Air resistance, air drag force. Force depends on the two things. One thing that the air drag force or air resistance depends on is the frontal area of the object. The frontal area of the object. So let's see. Does object like a pen here, pen falling in this direction versus pen that's falling in this direction. This pen, it's the exact identical pen, same way, same shape. But when it's falling in this direction, the air resistance, what would you guess? Do you think the air resistance is going to be the same as this, the sideways? Or if the pen is dropping down vertical, do you think the air resistance will be larger, same, or small? So the same object here, but in one case, this object is falling like this, or the same object that's falling like this. They're going to experience a different air resistance force. So the gravitational force is going to be the same because it's just the same object, right? Fg. And here you're going to have a Fg, same amount of a gravitational force. Either way. But I think you might have guessed that when you have a smaller front door area, the air resistance force, air drag force that's applied on it is going to be smaller compared to if you have a larger front door area. So in this case, it's going to be bigger air drag force. So it depends on cross section right here, how much frontal area of the object it's the same object, but they'll experience a different air resistance, air drag force. Another thing that air drag force depends on is actually the speed of the falling object. So let me see. It depends on the speed of the falling object. The reason why it depends on the speed of the falling object is that, let's say if the object is falling fast, bigger speed, that means that it has more chance of meeting more air molecules. And each time they make these air molecules make a collisions, it slows the object down, which acts like an air drag force. So the more air molecules that they need, the bigger the speed, you're going to have a bigger resistance. So let's see. Bigger the speed, larger air resistance. The reason why so is that the greater the speed, the greater the speed, the greater the number of air molecules on an object encounter per second. And therefore, the greater the force. Greater the force of molecular impact. So let's see. Let's think about in case for the what do you call that? Skydiving. Right. So so I'm going to talk about this. Let's think about a case for the skydiving. So then let's think about skydiving, right? You could be standing over here at the door of the helicopter. Actually, you don't have a door when you do the skydiving. You're just standing there. Immediately when you fall out from the helicopter, immediately you fall out. Immediately after you fall out from the helicopter, what is the force exerted on you? T equals 0. When you immediately fall out, your speed is 0. You start from rest. Then, if the speed is 0, there's no speed, then there's no air resistance. You're not moving, there's no air resistance. So the only force applied on you is the gravitational force. So you only have a gravitational force immediately after you step out from that helicopter. Then what happens a little bit later? So there's only gravitational force. So you're going to go down, right? Something like this. You're going to go down. Your gravitational force stays the same. It's the same gravitational force. But because initially you had a G and then that makes you accelerate. So your speed increases. As your speed increases, the air resistance going to be applied. What happens? So what happens a little bit later? A little bit later to this person that's falling. Still, so draw a free body, trying to draw a free body diagram of a little bit later than this second step. Then, how about gravitational force? Is that the same, bigger, smaller? Gravitational force still is going to be the same. But because you're going down, although you do have air resistance building up, you still have an acceleration downward, right? So therefore, the air resistance, that means you're going faster. Acceleration is not as much as G. Acceleration is less than G, but still it's pointing downward, right? That means that you'll have an increase in speed, not as much as G, but you're still increasing, accelerating downward. So when you accelerate downward, air resistance builds up, gets larger and larger and larger. So you go faster and faster and faster. And there is a point that here, at some point, the air resistance is going to be as large as the gravitational force. So at this time, this person has the magnitude of air resistance is the same as the gravitational force. Then what is its net force? Net force is 0. When the net force is 0, what's its acceleration? Acceleration is 0. So we call this condition, when acceleration is 0, we call this acceleration is terminated. So when the acceleration is terminated, what kind of a motion is it in when the acceleration is 0? Constant motion, right? Constant motion means constant speed. So the speed so after this, air resistance and gravitational force, they match. It's no longer accelerate, and the person is going to be in a constant motion, and it has the constant speed. And such a speed is called terminal velocity or terminal speed. So this person now is falling with terminal velocity or terminal speed. Constant. Constant speed, constant acceleration, because the acceleration is 0, right? So let's review here. When the person immediately falls down, there's only gravitational force. You don't have you're just starting from rest, so there's no air resistance. But as you go down, your speed increases. As the speed increases, air resistance also increase together. So until the person, and then the air resistance becomes as large as a gravitational force, then net force will be 0. And the person is no longer accelerating because the net force is 0, means the acceleration is 0. A person is in a constant motion, and such a condition, the speed of that, you have acceleration that's terminated. It's called terminal speed. So from here, from the very beginning till it reaches the terminal speed, all the way here, this person's is increasing speed. It's going faster and faster. Acceleration during this time is less than g, right? It's not as big as the free fall. And because as air resistance build up more and more, the acceleration is less and less. So here, the net force is Fg minus R downward. So acceleration is downward. And once the resistance becomes the same as the gravitational force, we call that to be a person is in a terminal velocity, and acceleration is terminated. So let me define the terminal velocity here. Terminal velocity is the speed of falling object when its net force is 0. So therefore, its acceleration is terminated. Okay. By the way, this person, the skydiver, he reached the terminal speed. So he's going to be in constant motion, but he's moving down still very fast. For example, skydiver, typical skydiver's terminal velocity is 200 kilometers per hour. 200 kilometers per hour. That's 55.5 meter per second. Each second, skydiver terminal velocity can be moving 55.5 meter each second. That's very fast. You definitely don't want to hit the ground with that such a massive speed. So what does the skydiver do? Yeah, skydiver is gonna shoot off the parachute. What's the parachute is for? What parachute does is that it increases the frontal area. So now you're gonna have larger air resistance by opening up a parachute. So let's see. If you go down, after you go down with the terminal speed, then you want to open up a parachute because you don't want to hit the ground so fast. Which direction? Okay. So then this person is going to finally open up a parachute. Let's see. Right? So by opening up a parachute, you're going to increase the air resistance. So you could have now you can have an air resistance that's larger than gravitational force. So gravitational force still stays the same, right? You're gonna still have the same gravitational force, but by opening up a parachute, you can have a larger than gravitational force air resistance, upward. So now, in this case, R is larger than Fg. So then the net force is upward. Then what happens to the acceleration? The direction of acceleration is now also upward. Because now you can have a larger air resistance than gravitational force. So it's gonna go point upward. If you have an air resistance that's pointing upward now, what happens to its speed? Speed is downward. Terminal speed initially is downward, but then now you have acceleration upward in the opposite direction, so you slow down. And then finally, you might be completely opening up a parachute. Then your gravitational force still stays the same. And the air resistance is so much larger. That's increase and increase and increase. So air resistance is larger then, but what happens? So then you slow down, you decelerate quite a bit. But can you keep decelerating? If you decelerate, right? So if you decelerate slow enough, what happens to your net force? You decelerate enough, then air resistance is going to be smaller because now you slow down, right? You slow down. If you have a decreasing in speed, air resistance decreases. air resistance decreases, and then at one point, if the air resistance decrease enough, air resistance decrease enough that it's gonna reach the second terminal velocity. Now again, it slows down. If you go decelerate enough, you're going to slow down, so the air resistance becomes smaller, and again you reach another terminal speed. The second time. And this terminal speed is going to be a lot smaller than the first terminal speed. So let's go over again. Jump off from the helicopter. Immediately after, you're in free fall. But then as you go faster and faster, air resistance starting to build up. When the air resistance becomes as large as the gravitational force, you're in terminal speed. But this terminal speed is really, really fast. When acceleration is zero, net force is zero, you have this terminal speed, and this is really fast. And you don't want to hit the ground with this fast speed. So then you're going to open up parachute. When you open up a parachute, you increase the frontal area of falling you. So then you can increase the air resistance. Now the net force is going to be upward, so you have acceleration upward. As the parachute goes up high, bigger, you're going to build up air resistance upward. But that means that you're decelerating in speed because you're still falling downward, and then acceleration is upward. That means you're slowing down the speed, and slowing down the speed means that less air resistance. So then the air resistance is going to starting to decrease, and it's going to be equals, at one point it's going to be again equals to the gravitational force. Then the person again hits the second terminal speed, and that's a lot smaller terminal speed than that this person had earlier. And this is going to be the safer way to land on ground. All right. Let's see. I'm going to ask you. So then, hope you kind of understand about the terminal speed and the air resistance, property of air resistance. So for example, about the terminal speed. The feather, and a skydiver. Let's compare the terminal speed of the skydiver and then a feather. So initial terminal speed that a skydiver can reach is, I mentioned, that's 200 kilometers per hour. That's really fast. Like it's like a fast train. It's too close to the edge, so I'll be rewriting. The terminal for the skydiver is 200 kilometers per hour. That's 55.5 meter per second. It's very fast. What would you guess for the terminal speed of the feather? Or like a paper, right? Paper or feather, it has a big frontal area, so it feels that air resistance all the time. So it reaches the terminal speed rather quickly, and it's very light. So when it's light, it matches the gravitational force rather quickly. So the terminal speed of the feather is like a few centimeters per second. So it's very small. Bigger. And I'm going to ask you this in a class, in a discussion. Which has larger terminal speed? It's an identical object here. Object, but falling differently. So the object that falls like this, or the object that falls like this. It's the exact identical object, but it's falling differently. A or B. Which one has a bigger terminal speed? Why? I'm going to ask you the different question in the class too. Now we're going to have a same size object, but mass 1 is the smallest and mass 3 is the largest. 1, 2, 3. Exact same size, same shape, but the mass of 3 is the largest. Which one has the largest terminal speed? Why? So I want you to figure out and explain why there's a different terminal speed, and then which one is going to have a bigger terminal speed. I'm gonna do another non-free fall, just specifically for the ball that's to be thrown upward for the non-free fall. So let's end this lecture here, and I'll see you again in part 2. So I'll see you in the class. Please try to do that problem, conceptual problem, and answer.